Welcome, everyone. This visualization tells the story of two powerful forces shaping our climate: compound climate extremes at the Earth's surface and the jet stream high above the atmosphere. Over the next few minutes, we'll explore how these two systems evolved together over the last 76 years through scientific visualization. Now, before we begin, let's first understand what compound extremes actually are. Climate studies have traditionally examined heat waves and droughts separately. However, the greatest impacts occur when both happen at the same time. These are known as compound extremes. When extreme heat combines with severe moisture stress, crops fail more rapidly, ecosystems become vulnerable, infrastructure is stressed, and risks to human health increase significantly. In other words, the combined impact is much greater than either event occurring alone. And over recent decades, these compound events have become increasingly frequent. So, how do we measure them? To quantify these events, we use the Dry-Hot Magnitude Index, or DHMI, an established metric in climate science that combines heat and moisture stress into a single value ranging from 0 to 1. Values above 0.60 indicate mild compound stress. Values above 0.80 represent dangerous compound events. And values above 0.90 indicate severe systemic risk. Throughout this visualization, every red sphere highlights a location where the DHMI exceeds 0.80, marking regions experiencing dangerous compound climate extremes. Now that we've introduced the metric, let's begin by looking at the surface symbol. Here, we're exploring 76 years of compound climate extremes, spanning from 1950 to 2025. On the left, you see a three-dimensional space-time visualization, where each horizontal layer represents 1 year stacked through time. On the right is the corresponding live two-dimensional surface map. As you watch, pay close attention to the red spheres. Each sphere marks a location where the DHMI exceeds 0.80. Notice how only a few hotspots appear during the early decades, and then, gradually, they become more widespread over time. So what does this tell us? Well, the long-term trend is quite clear. Compound climate extremes increase steadily throughout the entire 76-year period. No decade shows a reversal. The year 2006 exhibits the largest spatial extent of compound extremes. And after 2015, these events no longer fully disappear between years, suggesting that the climate has shifted toward a persistently higher baseline of compound condition. Now, let's move upward into the atmosphere. Having explored what happens at the Earth's surface, we'll now examine the atmosphere itself, all the way up to the jet stream. Here, the atmosphere is visualized using 5 altitude layers. Near the surface, wind speeds remain relatively low, between 5 and 25 meters per second, shown in blue. As we move higher through the lower and middle atmosphere, the winds become stronger and more organized. Finally, at the jet stream level, wind speeds reach 80 to 110 meters per second. The silver streamlines trace the three-dimensional path of the jet stream. Notice how the jet bends north and south. These large atmospheric waves, known as jet stream meanders, are one of the key mechanisms linking upper atmospheric circulation to the surface extremes we observed earlier. Now that we've seen the full atmospheric structure, let's zoom in a little closer. The 5-layer view revealed the jet as the atmosphere's dominant organizing feature. So now we focus specifically on the jet level and ask a simple question. Does this core remain in place, or does it meander? Here, we're looking specifically at the zonal wind, the east-west component of the jet stream, across 100 interpolated time steps. The contour lines represent wind speeds of 40, 60, and 80 meters per second. As the colors transition from blue to orange and finally magenta, they indicate increasing wind speed toward the jet core. Watch how the jet core continuously shifts north and south. When the jet dips toward the equator, it can trap warm and dry air beneath it, preventing the atmosphere from mixing efficiently. Across these 100 frames, we also observe a gradual poleward movement of the jet stream, reflecting one of the long-term signatures of climate warming. So, what does the jet stream reveal? 3 important observations emerge. The jet stream naturally meanders rather than remaining straight. These meanders can trap heat and moisture below them, creating favorable conditions for compound climate extremes. And over the 76-year record, the jet stream gradually shifts toward the poles, indicating changes in global atmospheric circulation associated with a warming climate. Now, let's expand our view even further. Here, streamlined tubes colored by wind speed reveal both the northern hemisphere and southern hemisphere jet streams simultaneously. The northern hemisphere jet appears more irregular, with stronger north-south oscillations. In contrast, the southern hemisphere jet remains more stable and predominantly east-west. Interestingly, many of the strongest wind corridors correspond geographically to the regions where compound climate extremes become concentrated, hinting at an important atmospheric connection. So far, we've explored the surface and the atmosphere separately. Now comes the most important part. Let's bring both datasets together into one integrated visualization. This animation synchronizes surface compound extremes with jet stream dynamics, advancing together from 1950 through 2025. The red spheres indicate locations where the DHMI exceeds 0.80, while the colored tube represents the evolving jet stream. During the early decades, the jet remains relatively straight, and the number of compound extremes is limited. As time progresses, the jet develops stronger meanders, and the number of extreme hotspots increases significantly. Take a moment to notice where these hotspots repeatedly appear. Rather than forming beneath the straight sections of the jet, they tend to cluster beneath the equatorward dips of the jet stream. Regions such as the Mediterranean, South Asia, and the Sahel consistently experience this behavior. These recurring jet stream patterns help trap heat and moisture, creating favorable conditions for persistent compound climate extremes. Now, let's pause on one particularly important year. This is the year 2006. It represents the largest compound extreme event observed in the entire dataset, where the strongest jet stream meander aligns directly above the largest concentration of surface climate hotspots. Finally, let's summarize what we've learned. Our study presents 4 main findings. Compound climate extremes increased steadily from 1950 to 2025, with the largest spatial extent occurring in 2006. The polar jet stream exhibits a measurable poleward shift over the observation period. Compound extreme hotspots consistently align with recurring jet stream meanders, particularly across the Mediterranean and South Asian regions. And finally, our visualization demonstrates how topological feature extraction using TTK enables efficient cross-domain analysis between atmospheric circulation and surface climate extremes. Thank you for watching. We hope this visualization provides new insight into how atmospheric dynamics influence compound climate extremes and demonstrates the value of scientific visualization for understanding complex climate systems.